A supermassive black hole mysteriously changed its direction and is now pointing at us. This unprecedented event left scientists both astounded and intrigued, as it is something astronomers have never seen in the universe. Even the galaxy housing the supermassive black hole has experienced a reclassification due to the shift in its core's jet direction. This discovery may pave the way for groundbreaking insights into black hole physics, particularly high-energy physics involving the behavior of subatomic particles at extreme energy levels. But the question is, how did astronomers find out that the black hole has changed its direction? How are the exotic, energetic jets produced in the first place? Finally, and most importantly, does the flip pose any threat to our planet? Before jumping into the discovery, it's important to know the difference between three critical things: an AGN, a quasar, and a blazar. An active galactic nucleus, or an AGN, is an exceptionally luminous compact region located at the center of a galaxy, emitting radiation across the entire electromagnetic spectrum. The AGN's intense radiation is generated by material falling into the accretion disk, a disk of swirling gas and dust that surrounds the black hole at the galaxy's core. The galaxy containing the AGN is referred to as an active galaxy, with this central object being called the nucleus. A distinguishing feature of AGNs is the presence of relativistic jets. When matter does not directly fall into the black hole, some particles accelerate to high speeds within a strong magnetic field, resulting in an ionized matter outflow along the black hole's axis of rotation. This typically emits radio wavelengths due to synchrotron radiation, forming twin narrow beams of high-energy particles known as jets, which can extend beyond the galaxy itself. These jets create two lobe-like structures on opposite sides, perpendicular to the accretion disk. If these twin jets are firing straight up in the plane of the sky as seen from our planet, we call them radio galaxies. If they are slightly angled towards us, we call them quasars. Finally, if these jets are pointing towards us, oriented in our line of sight, we classify them as blazars. One fascinating thing about these jets is that they validate a key prediction of Einstein's special relativity, relativistic beaming. This effect causes any source moving towards us to appear brighter, while any source moving away from us appears dimmer. Consequently, a jet relatively pointed in our direction will seem brighter due to the particles within it approaching us. Conversely, the jet directed away from us will appear dimmer as its particles recede. Take, for instance, the M87 galaxy. We can observe its 5000 light-year-long jet that is angled towards us. The matter within this jet travels at velocities nearing the speed of light, causing its properties to be governed by special relativity. However, the galaxy also possesses another jet oriented away from us. Due to relativistic beaming, this jet's intensity diminishes, rendering it less prominent and difficult to observe. However, in the case of 3C31, both jets are oriented almost perpendicularly to our line of sight within the plane of the sky. As a result, it is classified as a radio galaxy with both jets being visible. The upper jet is slightly angled towards us, making it appear brighter. Although astronomers have studied AGN jets for decades, this discovery left them astonished. For the first time in astronomical history, they observed the black hole's jet flipping its direction. An international team of astronomers discovered a galaxy with a jet that changed direction. The galaxy lies 657 million light-years away at a redshift of 0.047. For simplicity, let's call it PBC. The radio map from the Very Large Array Telescope reveals that the galaxy and its jet span approximately 1.2 megaparsecs, or around 4 million light-years, classifying it as a giant radio galaxy. To make this discovery, astronomers analyzed the light curves of the AGN at various wavelengths, studying the behavior of its emissions. Light curves are essentially plots of flux over time. During two observation periods in 2018 and 2019, they found that the AGN's core experienced three flaring events, which are radiation outbursts potentially caused by the reactivation of nuclear activity in the core. There were three important clues hinting that the black hole's jets flipped and are now pointing towards us. The first clue came from the optical variability of the blazar. Optical variability refers to the changes in flux and amplitude of peaks within the visible waveband. When compared to other blazars and AGNs, PBC's optical variability was consistent with the blazar population. The overlap between the two categories occurs because blazars could be classified as AGNs during their non-flaring periods. Despite this overlap, PBC's properties align with those of the blazar population. The second clue emerged from determining the jet angle, which is the angle of the jet relative to the observer's line of sight. By studying PBC's spectral energy distribution, astronomers created various models with different jet angles to match the observations. Among these models, the one with a 3-degree jet angle agreed with the findings. When the jet angle is 3 degrees, it means the jet is nearly pointing towards us, classifying the AGN as a blazar. The third and final clue came from examining the lobes and the nucleus. The radio image of the PBC galaxy reveals a critical detail. The central circular region represents the AGN's nucleus, while the two diagonally opposite regions are the lobes. There's no connection between the lobes and the nucleus, indicating that the core is not emitting radiation into the lobes. This suggests that the observed lobes are remnants of old jets, while the light curves and 3-degree jet angle correspond to a new pair of jets. The old pair of jets were in the plane of the sky, according to the radio image. Therefore, the 3-degree jet angle signifies a change in the jet's orientation. The most pressing question now is what caused the change in the direction of the jets. The exact reason remains unknown, but several possibilities have been proposed. There's a class of radio galaxies known as X-shaped or winged radio galaxies, which feature two pairs of jets in the plane of the sky, closely resembling an X shape. Among the misaligned pairs of radio lobes, the furthest ones correspond to the oldest jet ejections, while the lobes closer to the core represent younger and active jets. The PBC galaxy does not exhibit an X shape, possibly because the new jets are pointed towards us. Previous studies of X-shaped galaxies have suggested that black hole mergers or the engulfment of a smaller galaxy could be responsible for changes in jet direction. During a merger, the small black hole is deposited near the larger one, resulting in the incorporation or absorption of the smaller black hole's angular momentum by the larger black hole. This process causes a realignment of the larger black hole's spin axis. However, as compelling as this explanation may be, a 2017 study of the PBC galaxy found no evidence of merging activities. Other potential causes for the realignment of jet direction include the renewal of nuclear activity during which the jet axis precesses, the backflow of gas along the active lobes into the core, and the warping instability of the accretion disk. Further detailed studies may provide answers to this rare jet realignment phenomenon. Lastly, does this system pose any danger to us? Given that its jet is pointing in our direction, the answer is no. At a distance equivalent to 41.5 trillion times the distance between the Sun and Earth, the radiation from these energetic jets will have no impact on us. This is because as the radiation traverses this vast distance to reach us, it will lose all its energy due to redshift. So, there's nothing to worry about. This concludes another fascinating episode of the Sunday Discovery series.